In Chapter 7, we will be looking at various aspects of reactions, in particular two aspects, and that is the rates of reactions, how fast reactions occur, and in the second part of Chapter 7, we will look at chemical equilibria. But first, let us look at the rates of reactions. Some chemical reactions, as we all know, take place very fast, and some are very slow. For example, the reaction of glucose with oxygen, of course, as you know, glucose is sugar and is the source of energy for us. But its reaction with oxygen, if it's left outside, may take years, a long time. So here's the reaction: glucose with oxygen, that's an oxidation, combustion, to give carbon dioxide and water. It may take years for this reaction to go from reactants to products. On the other hand, there are some reactions that are very fast. They can be completed in seconds. So the summary here is that chemical reactions have a wide range of reaction rates. Notice the rates of the reaction from extremely fast to extremely slow. So some reactions take a long time, years, and some reactions take a very short time, like in seconds. Let us look at chemical kinetics. Kinetics here is basically the study of the rates of chemical reaction. So the key word here is rates. So let's imagine here you're trying to figure out how fast a reaction occurs. Key word here is how fast a reaction occurs. A good comparison is to imagine yourself driving on the highway. Your rate of speed is, for example, 70 miles per hour. So that means in 1 hour you cover 70 miles. So that would be your rate of speed. So here we're looking at the rate of a chemical reaction. So let's see if we can do that comparison. So if we have here chloromethane, and it is reacting with iodide ion. So in other words, two reactants to give the product here, iodomethane, to give a product. The question that we need to address here is how fast will this reaction occur, or can we give an estimate of its rate of reaction? To determine that, we can do the same comparison as with the speed. We can measure the concentration of the product per time. Okay, so it's the concentration per time. Let's apply that concept over here. So the same reaction, chloromethane with iodide ions to produce iodomethane and a salt. So at time 0, so before the reaction starts, before you mix these two things up, there is no product. Notice here the units of concentration here is moles per liter. So the concentration of the product here is 0. After some time, 30 minutes for example, you measure the concentration of the product, and if you get 0.12 moles per liter concentration of the product, you can say that the rate of this reaction is producing 0.12 moles per liter in 30 minutes. So let's put that in an equation. So 0.12 moles per liter minus 0, which would be the change in concentration, change in time, and of course here that's measured in 30 minutes interval. So you divide this number here by this number here, and you get here 0.0040 moles of product per liter per minute. So notice the unit. The rate of a chemical reaction is basically moles per liter concentration per time. In this case, minutes. So you can imagine a very slow reaction, the time interval would probably be years. A very fast reaction, the time interval would probably be seconds. But the bottom line is moles per liter per time, concentration per time. Let us now turn our attention to factors that affect chemical reactions. So in other words, if we have a reaction that goes very fast and one that goes very slow, what are the factors that dictate that one reaction goes very fast and the other one goes very slowly? So we'll look at these aspects here, and first one we'll look at is the molecular collisions. The molecules, the reactant molecules must collide for a reaction to take place, so we'll examine that in a little more detail. The energy of activation, which is the energy produced on collision. We'll look at the concentration of the reactants. If there's a large concentration of reactants, does that affect the rate of the reaction versus a reaction that has a very small concentration of reactants? We'll look at the temperature. Changing the temperature, does that affect the rate of the reaction? If we run the reaction at a very high temperature, will it be any faster or slower than running the reaction at a very low temperature? And we look at another concept called catalyst. If we introduce a catalyst into a reaction, will it speed up the reaction or will it slow down the reaction? So we'll look at these individually over the next few slides. First, let's look at molecular collisions. So for a reaction to occur, the reactant molecules, notice the reactants molecules must collide. They must come together. We call them collisions or molecular collisions here. Some collisions are very effective and some are not. Let's look at the illustration here. If we have two molecules here, green and purple, coming together in a head-on collision, that is a very effective collision to provide enough energy for the reaction to occur. If, on the other hand, the collision occurs sidewise or not head-on, it may not produce enough energy for the reactants to move on to product. So again, there must be effective collisions of reactant molecules for a reaction to occur. Let us look at this example here. So we have here water reacting with hydrochloric acid, HCl, to produce H3O plus and Cl minus. As you may recall, this is a reaction that we looked at before, an acid-base reaction where this is the base and here HCl is the acid. So the base here, being a proton acceptor, takes on this hydrogen over here to get H3O plus. So that is the reaction. The two reactant molecules here going to form two product molecules. For that to happen, however, there must be effective orientation of the molecules. So they must not only collide, but they must collide with the proper orientation. So as you can see here, this H needs to go onto the oxygen here. So an effective collision is the H end of the HCl bumping into the oxygen end of water. When that happens, the H here is transferred to the oxygen to produce here the product. So that's an effective collision, a collision that produces the products, which has the proper orientation. If, on the other hand, this molecule here has the Cl oriented oppositely from the previous collision, and it collides, it leads not to the product here, but to no reaction. So not all collisions result in products. Effective collisions that have the proper orientations lead to products. And effective collisions that have the correct amount of energy or sufficient amount of energy leads to the product. Summary. So if two species, notice we're talking about reactants, two reactant molecules, they must collide and they must have sufficient energy and they must have the proper orientation for a reaction to occur. What we're saying here is that not all collisions of two reactant molecules result in product. It's a fraction of these collisions that result in products. Let us look at another aspect here, the energy of activation. So let's define that. The energy of activation is the minimum energy required for a reaction to take place. So as you may recall, two reactant molecules A and B, they must collide, they must have sufficient energy after that collision, and they must have the proper orientation. If that energy is too small, no reaction occurs. If the energy meets a minimum energy, a reaction proceeds to give the product. Notice it's the minimum. So most reactions, one or more covalent bonds are broken, and of course that's by definition. A reaction is the making and breaking of covalent bonds, and there must be a minimum amount of energy required. That minimum amount of energy is called the energy of activation. So the energy of activation is the minimum amount of energy that's required from effective collisions for a reaction to occur. Let us look at this example. Could be any reaction, but let's look at this particular one. Hydrogen reacting with nitrogen to produce ammonia. Notice here, for a reaction to occur, this bond here must be broken. So energy must be supplied from the collisions of these molecules for this bond to be broken. This triple bond here, which is a very strong bond, as we know, must be broken. So these two molecules, they must collide and they must provide enough energy to break these bonds so that new bonds here can be formed in the product. So once again, the collisions of two reactant molecules must supply enough energy to break the bonds. And after the bonds are broken, new bonds are formed. I should point out here that whenever bonds are broken, energy is required. Whenever bonds are made, energy is liberated. So once again, if a bond is broken, energy must be supplied, typically from the energy of activation or from the collisions. And if bonds are made, such as these bonds, new bonds are made here, energy is liberated. As you can see from this reaction here, if it requires more energy to break these bonds and the energy liberated here is less, we have a situation here where we have put in a lot of energy, but we have not gained a lot. Let's look at the reverse. If we have put in a lot of energy here to break these bonds, and making these bonds releases a lot more energy, that reaction is called an exothermic reaction. So let's go over this again. The energy that's required to break the bonds, if that is greater than the energy required to make new bonds, that is called an exothermic reaction. So again, the energy required that's liberated from these bond making, if that is more than the energy required to break these bonds, that's called an exothermic reaction. Let's see if we can put this in a different format. So let's look at this reaction. So there's energy required. So this is reactant going to product. So in other words, what we're plotting here is the progress of reaction. So we start over here with reactant, and over time it continues until it gets to product over here. Let's look at what happens on this axis here. The energy. So these two molecules must collide, provide enough energy to break these bonds, and over here the products that are formed, the energy is liberated. If we have more energy liberated here, so that where there's a difference here, it's called an exothermic reaction. So notice whenever we have here the energy gap that's different here, it's an exothermic reaction. Some other aspects about this transition. So in going from reactants to products, the energy, minimum energy that's required for this reaction to occur is called the activation energy. Minimum energy. That's represented here by this gap. So this gap here is the energy of activation. At the peak here, it's called the transition state. That is the state of which the bonds are partially broken and partially made. So it's a description of this hydrogen being transferred to the product. So just a quick review that you should be able to recognize an energy profile for an exothermic reaction. Key here is that the reactant, the energy of the reactant is higher than the energy of the product. The energy of the reactant molecules is higher than the energy of the product. Another way of putting it is the energy of the product is lower, or the energy of the products is lower. Notice here, lower in energy than the reactant. That's an exothermic reaction. So the exothermic reaction, as we have seen from previous chapters, is a reaction that gives off heat. So when the reaction is done, heat is liberated. Heat is liberated. Let's look at the opposite. There are some reactions where the reactant, in going from reactant to products, heat is required. So in other words, you start here with the reactants, low in energy, and when the reaction is done, the energy of the product is higher. So we'd have to put in energy. This type reaction is called an endothermic reaction. At this stage, you should be able to recognize exothermic reactions and endothermic reactions based on the energy diagrams. If the energy of the reactants are lower than that of the products, that reaction is described as an endothermic reaction. This gap here is still the energy of activation, and this peak here is called the transition state. That's the state in which the reactants converts into the products. Okay, let us look here at concentrations. In most cases, the reaction rate increases when the concentration of either or both reactants increases. So in other words, if you have a reaction where you have reactants A and reactant B, if you increase the concentration of either reactant A or reactant B, the overall rate of that reaction increases. If you increase the concentration of both reactions, the reaction rate tends to increase also. So for many reactions, there's a direct relationship, and it is basically that whenever the concentration doubles, the rate of the reaction doubles. So if you double the reactant or one of the reactants, typically the rate of that reaction will also double. Here's a classic example. It's in the book. So if you look at steel wool that's burning in air, where there's a limited amount of oxygen, it burns like this. But if you should take steel wool and burn it in pure oxygen, it burns a bright white flame, because the concentration of oxygen is greater here than here in air. The steel wool burns much faster, much brighter in a higher concentration of oxygen compared to a lower concentration of oxygen, which is to the left. Conclusion: increase in concentration of either reactant or both reactants increases the rate of a reaction. Let's turn our attention to temperature. If you change the temperature of a reaction, will it affect the rate of that reaction? By observation, yes. For all reactions, if you increase the temperature of the environment, the rate also increases. As a rough rule, if the temperature increases by 10 degrees, approximately 10 degrees, the reaction rate literally doubles, or approximately doubles. Let's see why that happens. If you increase the temperature, there are more molecules moving faster. If they're moving faster, the energy on collision is a lot more. The number of frequency of collisions increases. So the factors that contribute to reaction rate here increases tremendously if the temperature increases. So once again, by increasing the temperature, molecules move much faster. And the fraction of molecules that will have enough energy to go onto products are much more. That means more molecules having enough energy of activation to go onto products, and hence the reaction is faster. Let's see if we can represent that using the energy profile. So if we have here a reaction where this is the reactant and it's going on to product over here as we have described here, this is the energy of activation. So if the temperature is pretty high, let's call that temperature 2, the energy of activation here is much smaller or low, because we have a lot of molecules that can go across this energy barrier to form product. So if this energy of activation is small, the reaction rate is fast. On the other hand, if the temperature is much lower, like in T1, the energy of activation here is much higher. In other words, we have fewer molecules colliding. We have fewer molecules colliding with sufficient energy to gain that required energy to go on to product. So the energy of activation here for a reaction at a lower temperature is much higher and therefore a much slower reaction. Conclusion. A reaction that has a higher temperature, T2, higher than T1, proceeds much faster because of the lower energy of activation compared to a reaction where T1 is a much lower temperature, which proceeds much slower. So conclusion, higher temperature increases the rate of a reaction. Lower temperatures decreases the rate of a reaction. Let us look at last factor here, catalyst. So let's look at a practical example. Formaldehyde in the presence of hydrogen over a long period of time will give you methanol. Reaction is very slow. But if we should introduce here a metal such as platinum or palladium or nickel, the reaction proceeds much faster at the same temperature. So we're not changing the temperature. We're just introducing here a metal. The reaction proceeds much faster. We call this a catalyst. So catalyst is anything that affects the rate of a reaction. It is not consumed in the reaction. It is not used up, because at the end of the reaction we still have platinum. So catalyst, another definition of a catalyst, is a substance that's used to increase the rate of the reaction but is not consumed in the reaction. So it increases the rate of the reaction. Let's look at that a little differently here. And so here again is that good old energy profile diagram. Reactants on this end going to products over here. So over time, that's why this axis is labeled as reaction progress, because we're going in this direction as that arrow indicates. So here's our reactant, high in energy. If there were no catalyst, it would have to go through this energy barrier to go on to products. So this reaction is very slow, as you can see here, because this energy gap here is, right here actually, is pretty high. Very slow reaction. But if you should introduce a catalyst, just as we did before in the previous slide, such as platinum or palladium, the reaction goes through a different path. a different path, lowering the energy of activation here, or a path that has a different and lower activation barrier to give the product. As you can see here, this gap here is much smaller, so therefore that is a fast reaction. So conclusion, a catalyst provides an alternate path which lowers the energy of activation, lowers the energy barrier, so that a reaction can take place much faster compared to the same reaction which did not have a catalyst. I think this is the last slide for this part of the chapter. So again, I know this is a lot of concepts here that you'll have to consider. So take your time and read your text as you go through these PowerPoints and this lecture. You may even have to pause at a different point until you gain the concepts here. But continue to study hard. There will be a quiz on Thursday over this aspect. It will just be on the concepts, no calculations. So make sure you understand the concepts and can answer questions that relate to the concepts here. So continue to study hard and get ready for that quiz on Thursday. Okay? Bye.